Good morning, good afternoon, good evening to all the participants from the different parts of the world. It's indeed a pleasure to be presenting for this conference, which talks about enabling of construction or reviving construction industry in the post-COVID 2020 world. So now the topic that I would be talking about is sustainable construction materials and methods for infrastructure and housing solutions. And I'll be presenting a uniquely Indian perspective on COVID, its impact, and post-COVID solutions for post-COVID recovery. So now, what are the challenges that construction faced during COVID lockdown? One of our biggest issues with the COVID-related lockdown was the construction sites were essentially closed off. The labor was essentially forced to migrate. We depend on a lot of migratory labor which come and work on our construction sites. And most labor then were forced to return to their home places, hometowns, home cities. And therefore, the construction sites essentially went barren. There was absolutely nobody to support construction there. So now that was the one part of the equation where there was mass movement of people that in itself created a lot of logistic issues in terms of moving people around. But most importantly, the construction activity ground to a halt. Now, I'm just showing you some photographs of construction, which was abandoned. Literally, it was abandoned halfway, and even construction to the point where shoring was put in place, but concreting was not done. So this is the state in which essentially construction was abandoned with the start of the lockdown. Now, in addition to that, there was a severe disruption of the supply chains. So when you talk about the production, whether it is production of cement, aggregate, the local supply chains were completely disrupted because transportation was affected, and so the local supply chains got disrupted. That created issues like local material shortages, and unused material lying on the production site. So there was basically material which was lying unused on the on the construction site, and there was also it was not being available or made available to the production of cement and other places where it was required. The third most important problem faced by the construction industry was liquidity. Essentially, money disappeared from the market, and construction industry in India tends to be more driven by cash. It's a more cash-driven economy, and that was severely impacted by the lockdown. Now, it was basically a scenario that played out over a period of 6 months, where starting from lockdown, when the migrant labor was forced to leave the construction sites, the construction stopped, the material supply chains were disrupted, so the material could not reach the construction sites, it could not even reach the cement production units, so cement production and other ancillary support units also came to a stop. But basically that from this lockdown, I think there is a chance for us to re-strategize construction. And what I see is opportunities for us to look at construction and probably identifying issues that will help us develop solutions. So the need of the hour is for us to pause and rethink some of these strategies, the way we have been doing construction over the ages. And of course, at this point of time, I'm restricting myself to an India-specific scenario. Now, in India, in specific, we have construction is a large employer in India. So it does employ a large number of people. And the employment base is primarily delegated to low and semi-skilled labor. So this is a mass employer of people with limited skill set. And it is relatively a low technology, or there is relatively low technology adoption in construction. So that's these are things that one has to keep in mind. So we cannot think of knee-jerk reactions when you're talking about solutions and opportunities. In terms of adopting mechanized construction, or in terms of going scaling up to where we reduce the labor, because it is, after all, an industry that does feed a lot of people. And while we're thinking of solutions with these constraints that we have, we also have to balance our needs, because India is going through a very rapid expansion, and there is a very great demand for housing. There's a large demand for infrastructure. In the next 10 years, we'll be making investments to the tune of $2 trillion in our housing and infrastructure market. So that has to be developed. We need solutions which are humane so that we can actually keep our employment base still large, but look for solutions that basically address the issues that have come up related to this lockdown. So some of the solutions that I would like to throw out there, since we're talking about post-COVID recovery, is to talk about local utilization of material. We have a lot of material, and now with the advanced production that we do, we rely a lot on supply chains, and oftentimes material is sourced from different places, and the production of something like cement takes place in a different location. So we need to look at materials being used for products, and probably look at more local utilization of materials, so that we can get away from or have a parallel system which can be sustained by local development, which is not does not depend upon the supply chains which bring in material from large distances. We need to look at things of employing labor locally. So this whole problem of labor migration would mean that if we can create employment in construction, of course, locally. Now, of course, the issue there is that typically the labor migrates from a rural setting to an urban setting, because most of the construction is in the urban setting. So now, how can we employ labor locally? We need to look at production which supports construction. That's what we need to look at. So look at more prefabricated products which are made with local materials, which can be done in a rural setting, so that these then serve to support the construction in the urban centers. We, of course, have to look at efficient construction. So we have to look at reduction in labor-intensive processes at the site. So these have to be supported by back-end production, which can then be done locally in the rural setting. So this is the kind of model that we probably have to think about, where we keep our employment base still large in construction, but then we have a lean construction site where at the construction itself, we are looking at more prefabrication, more precast materials that are being used, which also speeds up the construction, makes the entire construction process more efficient. And therefore, we are looking at a faster turnaround of constructed products. So what I'm going to do is now present on some of the opportunities and solutions of three specific things that we have worked on, which probably look at providing opportunities and solutions. The first one is with the use of excess fly ash locally in precast and prefabricated products to support construction infrastructure. And I'll present this in a little more detail in the next few slides. India has basically produces more fly ash than it can consume, and most of it is not being done in urban centers. So therefore, we have this construction material which can be utilized locally. So it can be utilized locally to produce precast elements and structural elements. So now, rather than move the fly ash across the country, use it locally to produce these precast elements right next to where it's being produced, which happens to be in most of the times in rural settings. And then those can then be used to support the construction happening in the urban centers. Then we are looking at local production of units using local materials, which basically are a value add and provide employment. So this is basically using local materials. And in specific, I'll talk about stone panel technology, which uses excess stones, which are produced locally in one specific geographic location in the southern part of India, to produce precast floor panels. And these precast floor panels can be used, can be deployed very rapidly for providing flooring in urban construction, in precast construction. Then the last thing I'll touch upon briefly is rapid housing solutions, because we do have a great demand for housing. And I'll just quickly present on the sandwich core technology, which can also be looked at for providing solutions for housing. Now, a quick background: cement, past, present, and future. India is right now the second largest producer of cement in the world, but our projected production, basically in 2050, if you are to go continue at the same trend, will make us the #1 producer of cement in the world. Now, some of the challenges we are currently facing with cement production are that our current limestone reserves are expected to last only 30 to 40 years. The energy requirement for cement is also quite large, and that is also one of those issues that has to be addressed. And the carbon footprint, of course, remains to be an issue. Now, with this background, if you look at the other scenario, where we look at coal consumption and fly ash generation. Now, the countries in the red that you see in this figure here, these countries in the dark red are basically the largest producers of fly ash in the world, the three largest producers. India is actually right now the second largest producer of fly ash in the world. Our coal consumption in India currently is about 536 million tons per year, and it's only expected to rise because we are commissioning more coal burning thermal power plants. Our current dependence on coal burning for production of electricity is to the tune of 70 to 75%. So that is bulk of our power production. But going forward now, with an increase in the power demand, we are going to rely, at least in the immediate next future, in the next decade, we are going to rely more heavily on coal burning power plants. So if you look at this graph here on the bottom right, you see the amount of fly ash that is being generated and the fly ash that will be generated in the future. Now, the green bars in this graph show how much fly ash is being utilized. And if you look at it, it is a small fraction. This includes all the fly ash that has been incorporated in construction and all the other uses that are there. So currently, a lot of fly ash is sitting in the form of fly ash dikes, fly ash ponds. So basically, this is fly ash that needs to be utilized. And like I mentioned before, this is sitting a lot of times in the rural centers of India. So now we need to look at solutions to fly ash, and that would help us kill two birds in one shot. That is, can we beneficially utilize this fly ash and do basically produce elements which can be used to support construction, rapid construction in the urban center. So that would basically allow us to utilize this fly ash beneficially, produce products in the rural setting, and those could be then used to support the construction in the urban centers. So if you now look at the fly ash in India, there is, of course, if I just go to the previous slide, this map of India here shows the different thermal power plants in India, and there is a almost equal geographic spread of these coal burning power plants across India. But what we did is initially to come up with solutions, we first wanted to understand this fly ash. So fly ash was collected from different power plants across the country, and it was analyzed. And what we found is that most of the fly ash, if you look at just the oxide compositions, there is a very small difference in the oxide compositions of this fly ash. But when we started using this fly ash in concrete, we found that the results were night and day. There was a big difference in the final strengths, the final properties that was achieved with these fly ashes. So to understand that, we had to do a higher level of characterization. The one unique thing about fly ash that's produced in India, or I should say the fly ash that is predominantly produced in India, most of it has very low lime content. It's very, very low. So most of it is class F fly ash. Now, what we did is we basically, from characterization, established the reactive silica and the reactive alumina in the fly ash. These are the two reactive elements in fly ash, which are most beneficial for use in cementitious systems or in alternate binders that are being produced nowadays. Now, if you look at the same 10 fly ashes, the blue line represents, or the blue bars represent the total oxide contents of the fly ash, and the green bars represent the reactive oxides. So if you see here, now the differences start showing up. While the blue bars are almost comparable for all fly ashes, in the green bars, there are a lot of differences in the reactive oxide content. First thing to note here, the reactive content is much smaller than the total oxide content. That means only a small portion of the total silica and the total alumina in the fly ash is available in a reactive form. And it can be as small as 13% of the total silica being reactive, and about 7 or 8% of the alumina being in the reactive form. So this is a lesson for us, where we realize that the fly ash, whether it is the production process, the boilers that are used, the temperature of processing, or the collection, there is fundamentally the fly ash we're using is of a very low reactive, has very low reactive content. So our next step was actually through this characterization, we established that from XRD-based analysis, we found that most of the fly ash is basically the oxides, the silica and the alumina, are locked in crystalline material. So if you look at this XRD, the graph that I'm showing here, a lot of the fly ash is locked in crystalline content of quartz and malite. Quartz is sand, which is very unreactive. So a large percentage of the fly ash is locked up in this unreactive forms. Basically, the reactive form is this glassy phase, which is shown in this orange line. So, and that is what we are interested in, but that content is low. So our next step was to look at the possibility of producing geopolymers with this fly ash. And basically for geopolymer production from a given fly ash, it is the reactive silica and the reactive alumina that are important. You take the fly ash, it is activated in an alkaline solution which contains dissolved silica. And basically when you subject it to a elevated temperature curing, what you end up with is a geopolymer, which is basically um, densely cross-linked network of silica and alumina, as I've shown here. Now, and this geopolymer, if it is produced from this alkali activation of fly ash, particularly the low calcium fly ash, tends to have a much higher strength than cement. It is much more durable, and it has very good fire resistance. So basically, it is an ideal material that can be used for construction. The only problem there is, of course, the temperature. So now, what we did is understanding the chemistry of the fly ash. We basically developed a process where using this low reactive fly ash, which is predominantly available in India, by optimizing the chemistry, by playing around, by determining the reactive oxide contents, by optimizing how much activators need to go in there, and activators are primarily provided in the form of sodium silicate and sodium hydroxide. Understanding the role of these in the entire reaction chemistry, we've been able to produce geopolymers which consistently give us strengths of about 80 megapascal. And basically, we've also reduced the temperature demand for curing down to 40 degrees Celsius. And that is basically the temperature that is common in summers in India. So basically 6 months of the year, the high temperature in most of India exceeds 40 degrees. So basically, we're able to achieve a binder that gives us 80 megapascal strength using fly ash, which is a waste material. And this entire process has been developed by understanding the chemistry of the process. Now, from there, then, now we are able to come to a point where we are able to collect fly ash from different thermal power plants and optimize the activator for this, and be able to produce cements which give us consistent strength and consistent properties. And these is done following the characterization of the fly ash in the that is obtained from these thermal power plants. And this cement would basically produce a geopolymer, which gives us consistently high strength and high durability. So while we are looking for support, so now this is fly ash that's being produced in across the country, in mostly in rural settings. So we are now looking to see if this material could be used to support infrastructure development. So now steam curing can easily be adopted, and it is being done for producing a lot of construction related products. So if you look at steam curing that is conventionally followed, we basically raise the temperature to about 85 degrees Celsius, hold it there for some time, 6, 8 to 10 hours, and then we cool down the product. And this is the ideal temperature for geopolymerization to happen. We can actually accelerate the geopolymerization and deliver the strength much quicker, as I had shown before. So because these geopolymers that are produced from fly ash have a very high acid resistance, they are ideal candidate for making these precast pipes, which can be used for sewage and even for transporting water in the urban setting. So now here is an idea of a precast product that can be made in close to the thermal power plant and can be used to supply the demand in the urban centers, or the requirement for infrastructure in urban centers. The other thing is also the tunnel liners. These are tunnel liners that are used to stabilize tunnels, and these tunnel liners again can be quickly made out of these geopolymers and can be used to support the infrastructure development. Now, another product that we're working on very closely with this fly ash is with developing cellular masonry blocks, which basically provide enhanced building envelope performance. Now, India is a hot tropical country, and for us, it is important that we keep the heat out of our houses. Now, most of the heat gains into our house happens through the walls, and basically, whatever we can do to increase to reduce the heat gain into the house would essentially involve trying to develop walls which have low thermal conductivity. And basically, what we are interested in is developing these bricks, and these bricks are used as infills inside a reinforced concrete frame. And basically, they are the outer envelope. This is the outer envelope of the building, which is exposed to the outer environment. Now, these bricks are currently made of what is known as autoclaved aerated cement blocks, which have a low thermal conductivity, but they're made of cement. Now, what we are, and I'm showing you the process of the autoclaved aerated concrete blocks, where cement is basically a cement-based matrix or air is entrained in the cement-based matrix in the form of tiny bubbles, and the entire cement block is autoclaved, and what comes out of it is the autoclaved aerated cement block. This AAC block is then used in making masonry, which basically makes the infills between the reinforced concrete frames. Now, what we are proposing is to use the same process of autoclaving, the process of autoclaving that is used for cement-based blocks, instead use geopolymer-based blocks. So we can use this fly ash, which is alkali activated, with the optimized binders, which delivers this high strength. We entrain it with this porosity in the form of tiny bubbles. We autoclave them, and we can produce masonry blocks. And we are even thinking of making these wall panels. Now, these are wall panels which basically can be used as infills, and this is technology that can readily be developed close to the production of the fly ash itself. And this is again would be used in employing a lot of labor close to where the production of these panels takes place, and can be used to supply the demand in these cities for infills in construction. So these are a few of those things we are planning with the fly ash, which basically decentralizes the production, takes the production closer to the where the fly ash is being produced, and generates employment in construction related activity close to where the fly ash is being generated. Now, the other two things I wanted to talk about is, one is coming up with use of local materials for construction. Here is a specific example of what we worked on with local materials. One of the common things that's found across India are stones. Stones are abundant in India, and stones from specific regions or areas like Tandur, Kota, Makarana. These are world famous for their quality, and have been used traditionally for different forms of construction. Now, Tandur is one particular stone which comes from a region in the peninsular part of India, where basically the stone is from a slate which is of a layered formation. It has traditionally been used in construction, and what you see here is a traditionally constructed house using this Tandur stone, and it's used as a roofing material and even for the construction of walls. Now, during the production of these tiles, which are used in construction as floorings, floor tiles, or sometimes even wall tiles, a lot of waste is produced. So we basically were looking at developing solutions to use up this waste, and also to deliver a precast construction product, which could be then used to support construction. So we came up with this innovative, eco-friendly precast natural stone composite floor system. Here we have the natural stone slab, which basically is cast in a ferrocement bed and supported on joists. So this is a precast unit that is made with these floors, with the stone slabs. And the stone slabs, initially we were using a square cut or rectangle cut stone slabs, but now we've moved to using irregular shaped stone slabs, which are essentially waste from the stone industry, and to develop these precast floor joists. And these precast floor joists can then be used directly to assemble the flooring system at a very rapid pace by in a total precast manner. And this is the assembled floor where all the slabs have been assembled. They're simply leveled, and you have a very quick flooring system that is developed by using these stone panels, which are produced in this one of these rural pockets in India. So the whole point is to set up this precasting unit, which would produce these precasting wall panels, and even precasting slab panels, which could then be used in urban centers to meet the requirement of flooring and for use as wall panels. Now, one of the advantages of these the floor panels as they're used is that because the top surface is a stone and it can be polished, one does not need to provide any finish to it. So the natural surface of the stone can be used as the finished surface. So thereby we also save material in the whole process. So the stone is acting as a structural material in this precast panel, and it also provides the finished surface after construction. So again, the construction, the production of these precast panels is being done in this rural part in Tandur, and the finished floor panels are shipped to the city. And one example here is where they were shipped to Hyderabad, which is a city, and used for construction in Hyderabad. So we are able to generate employment in the rural sector where the labor had migrated to, and at the same time keep the construction site in the urban center clean by adopting precast technology. So it's a leaner construction site in the urban setting. So just to show you some photographs of this integrated precast beam column system with the slab wall with the stone panel system that was used as floors. Now, the final thing I want to talk about is the 3D reinforced system for walls and slabs. Now, this is the wall panel system and even a slab system that has been developed, where basically we have 3D integrated wire mesh, which has this, which has a core which is made of expanded polystyrene (EPS). Now, what is done is that layers of concrete are basically cast on both sides of this EPS core, and we have wire mesh reinforcement on both sides, which serves as a reinforcement to this concrete layers on both sides. So this these integrated 3D wire mesh reinforcement of the EPS core is basically then assembled in the form of walls or slabs, and simply by concreting the two layers of concrete, the entire structure can be built. Now, this is basically being used a lot for prefabricated low-cost housing. The sandwich core technology has the advantage that because it has a EPS core, which has a very low thermal conductivity, it provides a very high thermal comfort. Now, of course, the limitation currently is that it's limited to small spans and simple structures. So it is ideally suited, and of course, it's ideally suited for modular construction. And it is a great solution for providing potential solution to housing problem in India, where we have a great demand for housing, both in the urban and in the rural sectors in India. So what is the advantage of this particular 3D reinforced EPS sandwich core technology? First is we can use local masons. So this labor that has migrated from the cities to the rural areas can be employed to make these panels. And these panels could also be used as precast panels for use in construction. So the production of the panel itself takes place wherever the labor is or wherever they have moved to. It, of course, provides very rapid construction. It has high thermal comfort. And overall, it's a lightweight construction. So there's saving in materials. So these are the three things that I wanted to present with India specific, which are India specific potential solutions for this post COVID disruption that was created. And the majority disruption had to do with the migration of labor, where labor moved from urban centers to back to rural areas, and basically trying to clean up the construction space so that we make the construction space in the urban settings which are more efficient, with leaner construction, with lesser labor, but at the same time keep the employment in the rural sector by providing opportunities there in the form of support, where basically support structures can be made there, shipped to the rural center, from the rural to the urban centers, and used for construction there. So with that, I'd like to thank you for your attention, and I hope everyone is keeping safe, and hope sometime soon we all get to see each other once this pandemic